If mitochondria are the powerhouse of the cell, then stars are the forges of the galaxy. Energy from our local star, the Sun, powers almost all life on Earth via photosynthesis. It keeps our atmosphere from turning solid, powers the weather, and drives cyclones. It's increasingly a source of electricity to keep our civilization running, but even without renewables, our energy was still from the Sun, just with a few million years separation. Few things on Earth aren't ultimately powered by the Sun. Stars need a massive and long-term energy source to stop them from collapsing under their own weight. A star's gravitational field is constantly trying to crush it, but the outward pressure from the energy the star is producing stops this from happening. This is the first of 4 fundamental forces we will come across when trying to understand stellar fusion. All of the universe's forces are involved in this. Gravity attracts all matter to all other matter and actually isn't very strong, but stars have an incredible mass. A main sequence star is a state of equilibrium between the two forces, that is sustainable from the 7 million years of the most massive stars to the 6,000 giga-years of a red dwarf, the lowest mass stars. That's longer than the 14 giga-years of the age of the universe. Hopefully none of this is a surprise, but how exactly are stars producing this crucial energy, and ridiculous amounts of it at that? Globally, humanity's power production is 27 terawatts. Tera is shorthand for 10 to the power of 12, and watts is joules per second. The Sun outputs 3.8 times 10 to the 14 terawatts. That's an insane amount of energy, which must be coming from somewhere. The process that releases that energy is hydrogen burning. A chemist would say that burning hydrogen produces heat and water, but here burning is being used to refer to fusion instead of combustion. Fusion is the process of combining light nuclei into heavier nuclei. This is related to, but different from, fission, where heavy nuclei are split into smaller nuclei. It's difficult to fuse nuclei, the energy barrier to do so is high. Thankfully, for an existence of a not boring universe, it's possible to overcome that barrier with high temperatures, high pressures, and some help from wave mechanics. To convert hydrogen into helium and get a bunch of energy in return is a multi-step and multi-route process. Let's start by having a look at what exactly we're burning and producing. The beginning of the elements, and what makes up the bulk of a star's mass, is hydrogen-1, which has a nucleus of just a single proton. This is the fuel of stars. It's usually found with its buddy, a single electron. As an atom, hydrogen-1 is much larger than just the proton at its centre. The electron is bound to an orbital around the proton, taking up a larger volume. But the temperature in stars is high, which gives the electron enough energy to escape from the proton and keep the two separated. We call a fluid of separated nuclei and electrons a plasma, which is the state of matter of stars. There are multiple isotopes of the element hydrogen. The most common hydrogen isotope in the universe is this, hydrogen-1. It's also the most common isotope of all the elements. The second isotope of hydrogen is deuterium, where a neutron is bound to the proton. It's the result of the first step of hydrogen burning. As you can see here, isotopes have the same number of protons, making them all the same element, but a different number of neutrons. Hydrogen 1 and 2 are stable. They don't spontaneously radioactively decay. For hydrogen, adding any more neutrons produces unstable isotopes, which will radioactively decay. However, tritium, which is the name for hydrogen-3, has a half-life long enough to have some uses for us here on Earth. The end result of hydrogen burning is helium-4, the most common isotope of helium. It has 2 protons and 2 neutrons. Helium-4 nuclei are also called alpha particles. This name comes from early radioactivity research. Larger nuclei can kick out helium-4 as part of alpha decay. If hydrogen burning/fusion is the process powering the Sun, where's the energy actually coming from? How much energy do we get from going from 4 protons to helium-4? We can find the answers by looking at the mass of the parts that make up helium-4. Protons unsurprisingly don't have much mass, just 1.7 times 10 to the negative 27 kilograms. To make things a bit easier, we can deviate from SI and instead work in atomic mass units. A proton's mass in AMU is 1.0073. The other nucleon, the neutron, has a very similar mass of 1.0087 AMU. Helium-4's mass is 4.0015 AMU. There are 2 protons and 2 neutrons in helium-4, so if we sum up the individual masses of the nucleons, we get 4.032. There's a missing 0.03 AMU. Helium-4 has less mass than the sum of the nucleons it's made up of. This difference is called the mass deficit, the difference between the mass of a nucleus and the sum of the masses of the nucleons it's made up of. The missing mass isn't just lost to the void though. Physics is all about conservation. If we multiply the mass deficit by the speed of light squared, we get an energy. The mass has been converted into energy. This is what provides the outward pressure to stop the Sun from collapsing, and what keeps life on Earth going. What we're using here is Einstein's well-known equation E equals mc squared. Like converting pounds to euros, this equation tells us the exchange rate between mass and energy. That rate is c squared, a huge number, so you're getting a lot of energy for your mass. With nuclear reactions, it becomes clear that there's not conservation of mass, but conservation of mass energy. The same thing happens with chemical reactions, just with very small mass deficits and lower energies, so we don't usually think of them as converting mass. In the early 1900s, there was debate over the source of the sun's energy. The prevailing theory at the time was gravitational contraction. As an object like a star or a gas giant contracts, the gravitational potential energy of the collapsing material is converted into heat. This is now known as the Kelvin-Helmholtz timescale. If this was the sun's only source of energy, then it estimates the sun's age to be 20 million years, which is what Lord Kelvin had done and was widely accepted to be the answer. But geologists disagreed with that timescale. By analysing strata, they had found that the Earth was at least 100 million years old. By 1904, studies of relative abundances of heavy radioactive isotopes in rocks pushed that estimate up to at least 700 million years. In 1919, Professor Francis Aston, a Cambridge scientist who was working on trying to make precise measurements of isotopes, built the first mass spectrograph, what we now call a mass spectrometer. He used this, and later on 2 more improved versions, to make precise measurements of the mass of as many isotopes as he could, for which he would be awarded the Nobel Prize in Chemistry in 1922. Among his first measurements were the masses for hydrogen and helium-4. With this new precision, it became clear that helium had some of this missing mass compared to hydrogen. Combined with mass energy equivalents proposed 15 years earlier by Einstein, a new source of energy had been found. Professor Arthur Eddington, unconvinced by the short lifetime for stars predicted by contraction, was particularly confident that hydrogen fusion had to be the answer. In his presidential address to the 1920 Cardiff meeting of the British Association for the Advancement of Science, he strongly defended this idea.
Gentlemen, the position may be summarised in these terms. The atoms of all elements are both of hydrogen atoms bound together, and presumably have at one time been formed from hydrogen. The interior of a star seems as likely a place as any for the evolution to have occurred. Whenever it did occur, a great amount of energy must have been set free. In a star, a vast quantity of energy is being set free, which is hitherto unaccounted for. You may draw a conclusion if you like.
With no knowledge of fusion, neutrons, or that stars were made up of primarily hydrogen, Edison had correctly proposed where a star's energy comes from. But there was a problem. The sun isn't hot enough. Fusion isn't easy. Protons give nuclei an overall positive charge. Like trying to force 2 magnets together, the positively charged nuclei will repel each other. This makes things difficult if you want to smooch them into being one. This is our second force, electromagnetism. It's much stronger than gravity and can repel as well as attract. It stops your hand going through the table and carries this video over Wi-Fi. The force nuclei feel doesn't simply keep increasing as they get closer and closer though. As they get very close, a different force becomes dominant, one that is attractive. This short-range force that's strong enough to overcome the electrostatic repulsion is the strong force. The strongest force is called the strong force. It's what binds nuclei together. The electrostatic repulsion when trying to fuse is known as the Coulomb barrier, as we can think of the Coulomb energy barrier as being like a wall the proton has to overcome to reach the other one. This wall is the point where on the outside, electrostatic repulsion will push the nuclei apart, and on the inside, the strong force will pull them together. In classical mechanics, a proton is like a ball. It can only reach the other side if you can throw it higher than the wall. In this analogy, being higher than the wall means having enough kinetic energy to reach the attractive region. You have to throw the proton pretty high to overcome this wall. To move the protons faster, you need to increase the temperature of the plasma. To overcome the barrier for proton-proton fusion, classically you need a temperature of 2 billion Kelvin. The core of the Sun is 16 million Kelvin. That's 2 orders of magnitude less than required. Classical mechanics couldn't explain how fusion in the Sun was possible. A new theory needed to be developed for us to understand how it works. When a wave meets a boundary, it can be reflected. If we send a wave packet at the wall, we can see it reflect back, like a mirror. But if you look on the other side of the barrier, there is a small part of the wave that has travelled through the barrier. Quantum objects such as protons are described by a probability density function, which is a wave, so it also has this behaviour. The PDF tells us how likely we are to find the proton in different locations of space. If the proton has enough energy, then there's a small chance we will find the proton on the other side of the wall. The proton has tunnelled its way through the barrier without needing to go over it. This tiny chance is all that's needed with the high density of protons in the star to allow fusion to take place at lower temperatures. How does the Sun go about burning hydrogen? It's too unlikely that 4 protons will collide and form helium in a one-step reaction. The actual process is a bit more involved. It starts with sticking two protons together. Two bound protons is an extremely unstable isotope, so we can't form helium-2 and build from there. Instead, another force gets involved. We have now come across all four fundamental forces in our quest to understand the power of stars. Gravity is what starts the whole shebang, collapsing interstellar dust to increase in density until fusion is ignited to fight against its unending pull. The electromagnetic force repels nuclei from one another, making it difficult to combine them, but the strong interaction will bind them together under the right conditions. And now we come to the last force, the weak interaction. With a range less than the width of a proton and the least strength of the four forces, the weak interaction doesn't come up very often. It's important for radioactivity and for this. Through the weak force, one of the protons can convert into a neutron, producing deuterium. Because the weak force is so not strong, this reaction doesn't happen very often. It's the slowest step in hydrogen burning. On average, a proton in the Sun will have to wait 5 billion years before it fuses with another proton. This reaction doesn't just produce deuterium though, it also produces a positron and an electron neutrino. A positron is an antimatter electron. It has the same properties as an electron, but a positive charge. It will annihilate with an electron in the surrounding plasma, converting the mass of both into gamma rays, the energy of which will be thermalized, converted to heat by the high density of electrons in the surrounding plasma. A neutrino is a very light particle that only interacts through the weak force and gravity. Without a charge or strong force interaction, they can pass straight through most matter unimpeded. After they are created by this reaction, they stream straight out of the Sun, and if they hit Earth, they'll go completely through that as well. Because most of the neutrinos never interact with any mass in the star, they carry away the 265 kiloelectronvolts of energy they're produced with out of the star, in the form of their high speed. This is actually very useful for us when trying to peer deep inside the Sun's interior. We can use large, sensitive neutrino detectors to catch the rare interactions these ghost particles from the Sun have with regular matter, and from that we can better understand how these nuclear reactions are taking place. The newly created deuterium will exist for around a second before it fuses with a proton, with the release of a gamma ray, to produce helium-3. Without the involvement of the weak force, this second reaction is far easier, and because it's easier than the first reaction, the equilibrium concentration of deuterium in a star is tiny. Deuterium is actually more abundant on Earth than in the Sun. About 0.015% of terrestrial hydrogen is deuterium, although this deuterium was produced just after the Big Bang, not in a star. What we've been following so far is the start of the proton-proton chain, the primary way that stars with a mass similar to the Sun do hydrogen burning. Now that helium-3 has been produced, the chain branches into 3 different routes to get to helium-4. The most likely route, at around 83%, takes 2 helium-3s and sticks them together to produce helium-4, spitting out 2 spare protons. The second most likely route, branch 2, consumes 15% of the helium-3s. This branch takes a few reactions. Instead of getting another helium-3, it's an alpha particle that fuses to get beryllium-7, which then can change to lithium-7 with the help of an electron, which then fuses with a proton to produce 2 helium-4s. For the last branch, we go back to beryllium-7. This last one is much less likely than the first two, at 0.02%. Instead of combining with an electron like in branch 2, instead it fuses with a proton to get boron-8. In this branch's penultimate step, boron-8 isn't fused with anything. Boron-8 is radioactive and can spontaneously beta decay into beryllium-8. One of the protons converts into a neutron. Beryllium-8 is also radioactive and will alpha decay in, on average, 82 attoseconds. That's times 10 to the negative 18 seconds. As I mentioned earlier, an alpha particle is a helium-4 nucleus. This leaves behind another helium-4, so we get the new alpha particle and a return of the one it used earlier. For branches 2 and 3, helium-4 is a catalyst. It's involved in the reaction, but it isn't used up by it. For the other set of reactions, catalysts are crucial. In the Sun, the proton-proton chain is the dominant source of energy, but there is also a second set of reactions that make up hydrogen burning, the CNO cycle. As the name suggests, the CNO cycle has no start or end. It is a continuous series of reactions that uses carbon, nitrogen, and oxygen as catalysts to produce helium-4. As these heavier nuclei are not used up by the cycle, they can take part in the reactions repeatedly. The Sun won't synthesize heavier elements like carbon until near the end of its life. Its supply of the 3 elements for the cycle is the same as what it was born with. Our local star is 3rd generation. It was formed from some material that was ejected by dead stars that contain these heavier elements. There are 4 CNO cycles. All of these reactions are happening simultaneously in the soup of the solar plasma. Products produced in one set of reactions can be involved in another set. The rate of all the reactions in the proton-proton chain and the CNO cycle closely depend on the temperature, and the temperature of a star depends on its mass. Larger stars are hotter. Although branch 1 is dominant in our Sun, as the star gets hotter, branch 2 will become dominant, and then at even hotter temperatures, the third chain takes over. As temperature increases, the higher Coulomb barriers of the heavier elements involved in the CNO cycle become less of a problem. So for large stars, the CNO cycle is more important than the proton-proton chain. So that's what powers the Sun and all other, main sequence, stars. At their hearts, a messy soup of the many reactions of the proton-proton chain and the CNO cycle, converting mass into energy, some of which ends up inside us. The wave-particle nature of protons allows them to bypass the insanely high temperatures that would otherwise be needed for fusion to take place. Stellar fusion is a slow, steady process regulated by the balance between gravity and fusion rate, giving stars their long to incredibly long lifespans. Thank you for watching. I hope you found it interesting to explore some of the details of hydrogen burning that aren't widely covered. If you'd like to see more videos like this or have any suggestions, then you can let me know in the comments below.